Okay, in this lesson, we're going to talk about two topics. First topic will involve a couple of theorems that have to do with proportions and triangles. The second topic will involve the perimeter and areas of similar figures. So let's get started with a little bit of review. So we've got a figure here. We've got big triangle ADE and then a smaller triangle ABC inside of it. Okay, we're asked which two triangles are similar. Let's see if we can pick out why they're similar. So we've got this little triangle here and this big triangle. We've got some measurements. These two parallel lines are important. We know that when two parallel lines are cut by a transversal, we've got corresponding angles that are congruent. So these two angles are congruent, and here's another pair of corresponding angles. So they're congruent. So we've got angle, angle, similarity. So these two triangles are similar. Okay, they ask us to redraw each triangle separately. So then we've got our triangle ABC here that has a side 5 and 7. And we've got the bigger triangle ADE that's got side 12. And for this side, we've got a 7 piece and an X piece, so if we just combine those for the whole side, then we get 7 plus X. Okay, then they ask us to solve for X. Well, we know that in similar figures that corresponding sides are proportional. So let's set up a proportion. Let's start with the pair of corresponding sides that we know, so 5 and 12. So if we go small to big triangle, and then our second pair of corresponding sides, small to big triangle. Okay, so there's our proportion. We want to solve for X. Cross multiply, we get 5 times 7 plus X in parentheses, and 7 times 12, which is 84. Okay, I want to distribute my 5, so we get 35 plus 5X. Okay, subtract 35 from both sides. We get 5X is 49. And dividing both sides by 5, X almost goes into 49 10 times, but it's 9 times with 4 left over. Okay, so there's our X value. So a little bit of review of ratios and proportions and similar triangles. Now let's look at our first theorem of the day, side splitter theorem. It says if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. Interesting. So what this is saying is that this piece to this piece is the same ratio as this piece to this piece. So let's write that as a proportion. So it's saying that FA to AU is proportional to FB to BL. Okay, so we can kind of just go down this side, make that a fraction, and then go down the other side and make that a fraction. We've got our parallel lines. This looks kind of like a triangle mid-segment, but we're not necessarily certain that it goes to the midpoints, but it's parallel to that third side. So we have this proportion, side splitter theorem. Let's see what we can do with that. Okay, number one says we now have an easier way. We've got this triangle here. We've got a missing piece here. Now, without the side splitter theorem, we would have to add these two and set up a proportion with the small triangle to the bigger triangle. But now with this theorem, we can just take 4 over 6 and set that equal to 6 over X. Okay, that saves us a lot of time, and we don't have to redraw the triangles. So let's solve for X. First thing I want to do is simplify this fraction. 2 goes into 4 twice, goes into 6 3 times. So then we can cross multiply. We've got 2x. 3 times 6 is 18. And what number can we multiply by 2 to get 18? It's got to be 9. Okay, so you do number 2 in your notes. So solve for x, set up that proportion, and box your answer. We'll talk about it in class tomorrow. All right, next theorem. The triangle angle bisector theorem says if a ray bisects an angle of a triangle, remember to bisect an angle means to cut it in half or to cut into two congruent angles. Then it divides the opposite side into two segments that are proportional to the other two sides of the triangle. So we've got a diagram here, triangle ABC. We've got an angle bisector AD. And this theorem is saying that we can set up a proportion that says that this side AB to this side BD, okay, so similar to the last one, the two sides on the left is proportional to the two sides on the right. So AC to DC. So these two sides, these two theorems are going to help us to solve some missing parts of triangles. All right, so let's look at an example. Example number 3. We've got a triangle. We've got an angle bisector in that triangle. And we're looking to solve for x. So let's set up our proportion. So the triangle angle bisector theorem says that if we've got that angle bisector, then this to this is proportional to this ratio, x to 8. So 6 is to 5 as x is to 8. Okay, let's solve for x. Let's cross multiply. 6 times 8 is 48. Set that equal to 5 times x. Okay, we're not going to get a nice neat whole number, but let's divide both sides by 5. 5 over 5 makes 1, so x equals, let's see, 5 goes into 48, 9 times with 3 left over. We're getting a lot of 9 mixed numbers here. All right, we can make a little box around our answer. Okay, one thing that's not in your notes that I want you to add in there is the corollary to theorem 8.4. It says if 3 parallel lines intersect 2 transversals, so we're not looking at a triangle necessarily here. We've got 3 parallel lines. Don't know how that guy got up there. Intersected by 2 different transversals. This theorem says the segments intercepted on the transversals are proportional. So we've got segments intersected A, B, C, and D. This theorem is just saying that A is to B as C is to D. Okay, real similar pattern with all 3 of these theorems and corollaries. So let's set this one up. A is to B, maybe we should write that up to the side. A is to B as C is to D. So if we plug in the numbers we know, if we want to solve for this D here, then we can say 3 is to 4 as 8 is to D. Okay, we cross multiply. 3D equals 4 times 8, which is 32. And if we divide both sides by 3, I believe we can fit 10 3's with 2 left over into 32. So D equals 10 and 2/3. Okay, so let's move on to the perimeters and areas of similar figures. All right, little quick review. Finding the perimeter and area of the following figures. Okay, assuming these are both squares, we've got 2 adjacent sides 5, 2 adjacent sides 8. Okay, to find the perimeter of a figure, we want to find the length around it. So if all sides are 5, we can do 5 times 4, because there's 4 sides, so that would make 20 centimeters. The area is side squared for a square, so 5 times 5 is 25, and we want our centimeters squared. Okay, for this bigger square, then we've got 4 sides of 8. So 4 times 8 is 32 centimeters squared, or excuse me, just centimeters, since we're talking about a length. And our area is going to be side squared, so 8 squared is 64, and that's in centimeters squared. Okay, so nothing revolutionary about that so far. But now, these two squares are similar to each other. They've got the same shape, congruent angles, just different sides, proportional sides. So in part A here, we're asked to write the lengths of their sides into a ratio. Okay, the lengths of their sides. So as a ratio, we've got 5 to 8. Okay, so remember, the ratio of the sides of two similar figures is their similarity ratio. Similarity ratio. Okay, so the similarity ratio is 5 to 8. It says write the perimeters of the two figures into a ratio. So the perimeters are 20 to 38. Excuse me, 20 to 32. All right, and remember, anytime we have a ratio, we want to see if we can simplify it before we move on. So 20 and 32. 4 goes into 20 5 times, and 4 goes into 32 8 times. Again, we can simplify these ratios with a colon just like we would a fraction if it was 20 over 32. So that's the same as 5 is to 8. Interesting. Part C says write the area of the two figures into a ratio. So the area of the first was 25. The area of the second was 64. Now you might be tempted to square root both of these to simplify it, but that would be changing the value. Remember, we only want to look for common factors. 25 and 64 don't have any common factors, so we can't simplify that one. Okay, it's kind of like you want to make it 5 to 8, but they don't have any common factors to simplify. So what do you notice? So what do you notice? Well, the similarity ratio and the ratio of the perimeters was the same. That's interesting. And then the area, since our area is side squared and our similarity ratio is the ratio of the sides, then it was just like that one squared to that one squared. Okay, it turns out that it doesn't just have to be squares that this pattern follows. It can be any similar figures. So Theorem 8.6 says, if the similarity ratio of two similar figures is A to B, then two things are true. Okay, the first thing, the ratio of their perimeters is also A to B. Okay, so the ratio of their perimeters is also A to B, so it's the same as their similarity ratio. The ratio of their areas is A squared to B squared. Okay, so let's look at a couple examples. First one, we've got a pair of similar figures. They look like trapezoids. It doesn't really matter. We know they're similar. We're asked to find the ratio small to large of the perimeters, ratio small to large of the area. So this theorem that we just talked about kind of says that if we can find the similarity ratio, then we immediately know the perimeter ratio, and then we can square both those to find the area ratio. All right, so similarity ratio. We've got corresponding sides here and here. So small to large, we want to go small to large. All right, and again, we want to simplify our ratios when we can. 3 goes into 6 twice, goes into 9 3 times. So our simplified ratio is 2 to 3. That's our similarity ratio, which is our A to B. Okay, our theorem says the ratio of the perimeters is also A to B. So our answer for question A is just going to be A to B. Question B asks us to find the ratio of the areas. So we take our A to B. Whoop, I don't want to write A to B. That's just silly. We'll write 2 to 3. Okay, if we square those, so 2 squared is 4, 3 squared is 9. There's the ratio of our areas. So without more information, we can't actually find the areas of these two figures. But we know that the ratio of the smaller one to the larger one's areas are 4 to 9. Okay, so let's leave those up for you. So we've got 2, 3, 4, and 5 on the back of your notes that you can practice. Circles work the same as polygons. Find the ratio of the perimeters and the ratio of the areas. We'll talk about those in class mañana.